When economists are analyzing the effects of changes in interest rate, they have to take into account a multitude of factors, often combining equations and then using the derivative to find the optimal solutions. Hi, my name is Tom Atwater, and in today's lesson, we will be learning the rules of differentiation. Let's dive right in. Derivative of a constant function. If f is the function with constant value c, then df dx, which is the derivative of c, is equal to 0. So the derivative of a constant is 0. The power rule for positive integer powers of x. If n is a positive integer, then the derivative of x to the n is equal to n times x to the n minus 1. All right. Next rule, the constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative of c times u is equal to c times the derivative of u. All right, let's look at the sum and difference rules. If u and v are differentiable functions of x, their sum and difference are differentiable at every point where u and v are differentiable. At such points, the derivative of u plus v or u minus v is going to be equal to the derivative of u plus the derivative of v, or the derivative of u minus the derivative of v. All right, what we should do is try some examples using those particular rules. So find the derivative, and we have two particular equations. Y equals 2x plus 1. So let's do that first. The derivative, dy dx, is going to be equal to, looking at this, the understood power there is 1, although we don't usually write it. So we have to apply the power rule, which says to bring this down and multiply it. Now, there's a constant there, so we have to multiply 1 times 2, which would, of course, be 2, and then x raised to the power of 1 minus 1. We have to take 1 away from it. Well, x to the 0 is just 1, so we just get 2, and then we have to take the derivative of a constant, but we just said that the derivative of a constant is 0. So the derivative of y equals 2x plus 1 is 2. Let's look at the second equation I have. We're looking for the derivative, dy dx is equal to. Once again, we have to apply the power rule to this example. So we have to bring the 3 down and multiply it. So 3 times this means that the 3's will cancel, and we will just get x squared. Then we apply the power rule here, and the same type of thing is going to happen. When we bring the 2 down, it's going to cancel there. And that's going to leave us with just plus x. And then finally, the derivative of x, we've already seen up in here, the derivative of x is just 1. So the derivative of this function is x squared plus x plus 1. Let's try another example that uses these rules as well as what a derivative means. Find the points on the curve below where the tangent is parallel to the x-axis. The equation we have is y equals 2x cubed minus 3x squared minus 12x plus 20. So we need to find the derivative of this function. So y prime will be equal to, bring the 3 down, multiply, we get 6x squared. Then, same thing here, we get minus 6x. And for the negative 12x, we just get negative 12. And of course, remember that the derivative of a constant is 0. Now, for the tangent line to be parallel to the x-axis, the slope has to be 0, right? Because that's what the x-axis has. And so therefore, the first derivative that we've just calculated here must be equal to 0. So we will set this equal to 0 and solve it. Let me get a clean screen for this. And we had that 6x squared minus 6x minus 12 will be equal to 0. So now what we do is solve this. We can do one thing, which is divide through by 6, and that'll give us the equation x squared minus x minus 2 equals 0. And that'll just make it a little bit easier to solve it, because now we can factor it as x minus 2 times x plus 1. And now we set each of those factors equal to 0, and we'll get x equals 2 and x equals -1. And so what that means is that there are two particular x values where the slope of the tangent line will be 0. And to calculate those points, we would have to plug 2 back into the original function, that original equation. And if we do that, we'll get that y is equal to 0. And we then have to plug in for the x equals -1, plug that into the original equation, and that'll give us an answer of y equals 27. So those are the 2 points at which the tangent would be parallel to the x-axis. Now, let's move on to a rule for differentiating a product of functions. The product rule tells us that the product of two differentiable functions, u and v, is differentiable, and the derivative of u times v is equal to u times the derivative of v plus v times the derivative of u. Let's try this out. Let's do the example, find the derivative by applying the product rule, and then let's multiply the factors first and then do the differentiation by the rules that we just looked at earlier. But let's first do it by applying that product rule. So we have y is equal to x plus 1 times x squared plus 1. So the derivative y prime is equal to the first, which is my u, times the derivative of the second. So the derivative of this would be 2x, and of course, the plus 1, it's a constant, it is 0. So therefore, we have plus, taking v, which is x squared plus 1, and multiplying that times the derivative of the first one. But the derivative of the first one, of course, is just 1. So when we simplify this, we have to multiply 2x times x and 2x times 1. And then, of course, the 1 here isn't going to change that. We're just going to have x squared plus 1. So therefore, y prime, calculated this way, is going to be equal to 2x squared plus x squared is 3x squared. Then we have the plus 2x, and then we have plus 1. So that's the derivative that we find by using the product rule. Well, let's do the other way, which is to multiply out the two factors and then differentiate. So if I do that, when I multiply this, I'm going to put my answer right here. So it's y again. And that's going to be equal to x cubed, right, plus, when I'm going to have an x squared, when I multiply, this is my x cubed, then I'm going to have an x squared, then I'm going to have the x times 1, which is my plus x, and then finally 1 times 1, which is my plus 1. Let me make that a little cleaner for you. That's 1. Okay, so now let's differentiate by the power rules that we looked at. This y prime will equal, bring down the 3, so it's 3x and then squared. Then bring down the 2, so we get 2x and then for the derivative of x is just 1. Well, surprisingly, we get the same exact answer that we got by looking at it doing the product rule. So you can see you have a choice there. Now, let's move on to something called the quotient rule. The quotient rule says at a point where v is not equal to 0, the quotient y equals u divided by v of two differentiable functions is differentiable, and the derivative of u divided by v is equal to v, the denominator, times the derivative of u, which is the numerator, minus u, the numerator, times the derivative of v, the denominator, all of that divided by v squared, divided by the denominator squared. Okay, so the equation we have is y equals x squared over 1 minus x cubed. And we want to find the derivative of it, which means to apply the quotient rule. So dy dx will be equal to the denominator times the derivative of the numerator, which is times 2x, minus the numerator times the derivative of the denominator. And the derivative would be minus 3x squared. And remember, the derivative of 1 is just 0. Now that's all over 1 minus x cubed quantity squared. If you simplify all that down, you'll find that the derivative dy dx is equal to x to the fourth plus 1 all over 1 minus x cubed squared. And that's your derivative via the quotient rule. Let's use the derivative as a concept for work and take the next example, which is find the tangents to Newton's serpentine, which is y equals 4x over x squared plus 1 at the origin and at the point 1, 2. So what we're going to do here is to find the tangent lines, we of course have to find the derivative. And so to find the derivative, we're going to have to use the quotient rule. So let's do that first. Y prime is going to be equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And that's all over the denominator squared. If we look at the top of this and simplify it a little bit, we get 4 times x squared plus 4 minus 8x squared. We will leave the bottom as is, x squared plus 1 quantity squared. Because now, if we want to find the slope of the tangent line, we now know that this is our slope, which I can simplify a little bit more because of my x squared and my minus 8x squared. So I get y prime is equal to negative 4x squared plus 4 over x squared plus 1 quantity squared. All right, so what we would do next is to actually find the slopes at those 2 points that we were given. The origin is the first one. So let me go to a clean screen so I have some more room. All right, so what I found was that y prime was equal to negative 4x squared plus 4 all over x squared plus 1 quantity squared. And now for the point of 0, 0. When I plug in 0 here, I will find that the slope is equal to 4. And of course, we already know that the y-intercept is 0, so my equation for this tangent is y equals 4x. For my other point, which was 1, 2, when I plug 1 into that, we're going to find out that the slope is equal to 0. The y-intercept for this is, of course, going to be 2, because if the slope is 0, it's a line parallel to the x-axis, in other words, horizontal, and it has to go through the point 1, 2. So my equation is y equals 2. So those are the two tangents that we calculated as against Newton's serpentine at the point 0, 0 and 1, 2. Let's look at another rule, which is called the power rule for negative integer powers of x. If n is a negative integer and x does not equal 0, then the derivative of x raised to the n is equal to n times x to the n minus 1. And yes, you probably recognize that, and we're just reapplying it for negative integer powers. Let's try an example of where we would use the power rule. So what I would like to do is find an equation for the line tangent to the curve, y equals x squared plus 3 divided by 2x at the point 1, 2. And we're also going to look at this to support our answer graphically. We can split this up as x squared over 2x plus 3 over 2x, and then simplify that a little bit so we get y is equal to x over 2 plus 3 halves times x raised to the minus 1. And so that way we can apply that power rule for negative integer powers. Y prime is going to be equal to, well, the derivative of x is just 1, so we get 1/2. Now we bring this down in front to multiply, so we have minus 3 halves, and it would be x raised to the negative 2. And so that would give me y prime using the power rule. So now what we want to do is we want to find the slope at the particular point. And so we have to plug in that x is equal, we have the point 1, 2. So we plug in the 1 into this equation, and we will get that the slope is going to be equal to negative 1. So the y-intercept at this particular case is going to be equal to 3, and you find that by substituting in 0 for x. So the equation that we're looking for is y equals negative x plus 3. Now, let's see if the graph supports that. So if we look at the point 1, 2 and the tangent line there, we can see that the tangent line has a slope of negative 1 because it's negative 3 over 3, and of course the y-intercept of 3. So the graph does, in fact, support what we were trying to do. Now, let's move on to higher order derivatives. We will discuss them by means of doing an example. I want to find the first 4 derivatives of the polynomial y equals x cubed minus 5x squared plus 2. So my first derivative, y prime, would be 3x squared minus 10x, and of course the derivative of 2 is 0, the constant. My second derivative, y double prime, is going to be equal to, we just take the derivative of this. So it would be 6 minus 10. And for the third derivative, y triple prime, that's going to be equal to 6. And finally, the fourth derivative, y quadruple prime, is equal to 0 because the derivative of a constant is 0. So finding higher order derivatives is just a matter of taking the derivative of each successive problem, each successive derivative. Well, now it's time for you to try a problem on finding the higher order derivatives. I would like you to find the first 4 derivatives of the equation y equals x to the 4th plus x cubed minus 2x squared plus x minus 5. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution.
3, 2.
All right, let's find out how you did with this. So I wanted you to find the first 4 derivatives. So y prime is going to equal 4x cubed plus 3x squared minus 4x plus 1. So that would be your first derivative. To find the second derivative, it's y double prime. You simply take the derivative of the polynomial here, so we'd be 12x squared plus 6x minus 4. To find y triple prime, we would, again, take the derivative here, so we get 24x plus 6. And then finally, the fourth derivative is equal to 24. So that's how you find higher order derivatives. All right, in this lesson, we explored derivatives, higher order derivatives, and how to apply those in terms of finding tangent lines and the slopes of tangent lines. Be sure to work the exercises that your teacher assigns, and we'll see you next time.